Good afternoon, everyone. It is my pleasure to present my topic today. My name is Moonsu Park. I am the PhD student in KAIST. And today's topic is non-matching mesh treatment in the integrated hydrostatic and dynamic analysis of floating structures. Let's get started. Here is the overview of my presentation. I am going to split my presentation by parts like this. From manufacturing to disposal of ships and offshore structures, there are many types of loads acting on floating structures during the life cycle, such as hydrostatic load, hydrodynamic loads due to the waves, cyclic loads from main engine propeller, ice load, and others. Among those various loads, I focused on hydrostatic force and wave load. There are many ships and floating structures in the world. To design the floating structures, hydrodynamic analysis of the floating structure is essential. Typically, the dynamics of a floating structure has been based on the assumption of rigid motion, because it could produce acceptable results with more simple and efficient analysis. But as the size of ships and floating structure is getting larger, the hydroelasticity effect becomes more important. And for the hydrodynamic analysis, hydrostatic analysis should be performed. So the modeling for the hydrodynamic analysis is required. Hydrostatic analysis and dynamic analysis are conventionally performed in the following chart. Hydrostatic analysis is performed using Hall geometry and mass information. Using the wet surface information obtained from hydrostatic analysis, hydrodynamic analysis is performed by creating a model for hydrodynamic analysis. Various external loads obtained in this way are applied on the structure model to obtain the response of the structure. For this process, separate models are required for hydrostatic, dynamic, structure analysis. Our research goal is the development of non-matching mesh treatments for hydrostatic and dynamic analysis using a single mesh model in this chart. Let me explain the problem description and assumption. The left figure shows the problem description considered in this study. It is assumed that the floating structure has a homogeneous, isotropic, and linear elastic material, and the fluid flow incompressible, inviscid, irrotational. Thus, the potential flow theory can be used. Also, all the waves are gravity waves with a zero atmospheric pressure assumption, and the surface tension effect is ignored. To clarify the state of the problem, we classify the state as three states, namely initial state, hydrostatic equilibrium state, and hydrodynamic equilibrium state. After the hydrostatic analysis is performed by applying loading information to the initial mesh model, the posture of the floating structure can be obtained in static equilibrium state. At this time, the initial mesh model can be posed as a mesh model in a matching state that matches with the free surface as shown in the left figure. However, in most cases, the mesh model doesn't match with the free surface as shown in the right figure. In order to perform hydrodynamic analysis, in the case shown on the right, it is necessary to modify the mesh model. in the case of a simple shape, it is not difficult to modify it, but in the case of the complex shape, it takes a lot of time. This is the formulation. Through the assumptions and conditions in the previous slide, we can derive a matrix formulation for the steady-state hydrodynamic problems by discretization. The finite element method is employed for the floating structures, and the boundary element method is used for the external fluid. Each term expressed as follows. The terms in the red box that requires of non-matching mesh treatment. To handle the non-matching mesh problem without modifying the initial mesh, an effective numerical integration technique is adopted. We consider 4 different cases depending on the number of wet nodes in a 4-node element. Numerical integration is carried out by using a temporal node appropriately for each case. In order to verify the proposed method, 3D biology model is used to the analysis. The commercial tools ANSYS Aqua is used to verify proposed method. Analysis results using various methods were compared. The ship structure is modeled using 4-node elements. The total number of elements used 3,920. Other conditions are like this, and 2 wave directions are considered. And also matching and non-matching mesh model are considered. The result from proposed method, Aqua result, and calculation experiment of pink stars are compared. The surge and heave result from various methods are in good agreement. In the case of pitch motion, there was a slight difference in low frequency. Zhou et al. Inferred the difference between the test result of the pitching motion and the calculation as an error in the radius of gyration for the model test. This is the result for incident wave angle is 45 degrees. We drew 6 degrees of freedom motion RAO result. All the results obtained from the present formulation and ANSYS Aqua are in good agreement. We carried out the hydroelastic analysis to investigate the hydroelasticity effect. Results are indicated at the 3 points on the bottom of the ship, stern, center, and bow. We also plot the hydroelasticity result of the proposed formulation for the rigid body case. Then we can investigate the hydroelasticity effect. This is conclusion. A non-matching mesh treatment method has been developed using efficient numerical analysis integration in hydrodynamic analysis. Through this, hydrostatic and dynamic analysis are performed using a single mesh model. The proposed method is verified through a numerical example, and the numerical results show good agreement with those obtained using ANSYS Aqua. Thank you for your attention. Thank you.